All right. Happy Wednesday. As a reminder, we do not have class tomorrow. There is no class tomorrow. It is Veterans Day. So after today, it is the weekend. A few other reminders. Test 4. Remember, I extended that due date up until today. So that's due tonight at midnight, along with the week 10 homework. I extended that due date until tonight. So you have up until tonight to do it. Make sure you get that done. Test 5 opens up on Friday. So something to keep in your radar. That's going to cover all of last week's material and this week's material. We need to finish up yesterday's lecture, and then we'll go on to talk about this worksheet that I sent out. But we're going to first go to yesterday's lecture and finish that conversation, and then move forward. Oh man, am I tired? Okay. Oh, there's like not enough coffee in the world right now. All right, so we went to go talk the. Let's just have a little coffee. We went to go talk about oblique asymptotes. We got to draw a picture of one, but we didn't talk about how we find them. So oblique asymptotes, they function a lot like horizontal asymptotes. So the functions are going to hug them on their way off the screen to the left and to the right. With horizontal asymptotes, that line is straight. With oblique asymptotes, sometimes called slant asymptotes, they're not straight lines, they're lines with slope. But they function will hug the oblique asymptote as it leaves the page. Oblique asymptotes only happen if the degree of the numerator is exactly one more than the degree of the denominator. And in order to find an oblique asymptote, you have to do long division or synthetic division if it's a situation that you can do synthetic for. And the oblique asymptote is the quotient after division has been done. So I'll write that all down. So if the degree of the numerator is exactly one more than the degree of the denominator, then there's an oblique asymptote at y equals the quotient after doing long division. So let's do an example where we find the oblique asymptote. I think I'm going to do a different one. Yeah, we'll do this one. All right. So find the oblique asymptote. We have g of x is equal to negative x squared plus 2x plus 3 all over x plus 2. We're going to do long division. You could do synthetic division in this case, but I'm just going to go ahead and do long division. I'm going to do long division here. X plus 2 is my divisor. My dividend is negative x squared plus 2x plus 3. So I'm taking that leading term of the dividend, and I am dividing it. This pencil is like slightly thicker because I changed it to do graphing and I don't feel like changing it back. So I'm just going to leave it at the slightly thicker width. This is negative x. Take negative x and multiply it by your divisor. You get negative x squared minus 2x, and then we change the sign, plus x squared plus 2x. We get 4x plus 3. We're taking the leading term of what's left over, dividing it by the leading term of the divisor, which is x. We get 4. And we could actually just stop right here. We could just stop because this right here is our oblique asymptote. Okay? We don't need to do any of the rest. We don't need to find the remainder. If we wanted to, we could, I guess, we could do that. But it is ultimately unnecessary because the remainder doesn't do anything for us when it comes to finding oblique asymptotes. So for this guy, there's an oblique asymptote at y equals negative x plus 4. And I guess what I probably should have said at the very beginning of this problem is that we know there's an oblique asymptote because the degree of the numerator is exactly 1 more than the degree of the denominator. So the degree of the numerator was 2, and the degree of the denominator was 1. So the numerator's degree is exactly 1 more than the degree of the denominator. And that's how you find oblique asymptotes. Any questions on the oblique asymptotes? We're hopefully going to get to a problem where we get to do one. I hope we get to it. Fingers crossed. Okay. So then the last thing to talk about before we actually do the worksheet is holes in graphs. These are also known as removable discontinuities. Removable discontinuity. And these are just what it sounds like. These are holes in graphs. So I'm just going to put some like random asymptotes in here. Right. These could occur anywhere. I'm going to go ahead and put the hole right here. So what you end up having is just a hole in the graph. Yeah. We call it a removable discontinuity, but it's just it's a hole in the graph. And these holes happen when there's a common factor in the numerator and denominator that cancels. So we had talked before about with vertical asymptotes, how we factor the numerator and the denominator, we cancel the common factors, and then we set the denominator equal to 0. So like in this very first problem we did here, we canceled out this x minus 3, and it didn't give us a vertical asymptote. We only got asymptotes out of these guys. And I said something happens with this, but we'll talk about it later. The something that happens is it creates a hole in the graph. When you cancel a factor out like that, it creates a hole. So if the numerator and denominator have a common factor that cancels, then there's a hole in the graph at that factor's 0. Factor's 0. So here's how it works. You're going to find the 0. Go back up to this guy here. You find out what the 0 would be. So in this case, it would be the 3. And then you take that x value, that's the x value of the hole, because the hole is at a certain point. That'll give you the x value. And then to find the y value, you take that value, 3 in this case, and you plug it right back into the canceled form. Right, so holes happen at what the point would be after canceling has taken place. Let's look at an example because that's going to make it easier. So here, we're trying to find the location of the hole. What you're going to notice is that these x plus 3s are going to cancel. And because the factor in the numerator and denominator canceled, we know that there is a hole, and it's going to be at x equals -3. So we're trying to find the location of this hole. We know that the x value is -3. The x value is -3. When this simplifies, we have 2x over x plus 1. To find the y value, we plug -3 into this canceled version of the function. So plugging in -3 for x. So we have, I don't like how crooked that -3 is. 2 times -3 over -3 plus 1. So we have -6 over -2, which is +3. And that is the location of the hole. So you get your x value by looking at what factor canceled and finding that 0. So it's -3 because that was what canceled. And then to find this y value, you plug in the x value to the canceled form. And just like that, and just like that, it's over. You have found the hole in the graph. All right, so what we're going to do now is we're going to combine everything we talked about and actually graph some rational functions. We're going to actually do it. I have sent out this worksheet. Hopefully you have it printed off. Here. The front page goes over almost everything that we talked about, except for I forgot to put holes on here, but it's fine. Oh, sure. While you're doing that, there's something I want to change on that worksheet anyway. Sorry, I don't have Zoom open for just a second because I realized something I wanted to fix on here. What I want to do, save. Yep, no problem. All right. So what I was just fixing on this worksheet, it's not fixed on here, but I was fixing it on my computer. With these horizontal asymptotes, I have it so like it's like degree of numerator less than degree of denominator, horizontal asymptote at y equals 0. But instead of having that picture first down here, it's second. So like logically, it doesn't flow as well. So anyways, what I just did on my computer is I swapped the order of these two so that it's this one first, then that one, then this one, just to make a little bit more sense. Okay. Not that it helps you guys, but for my future times that I use this worksheet. All right. So today we are graphing rational functions. Graphing rational functions. And this is a summary of everything we talked about yesterday: how to find the domain, how to find the x-intercepts, how to find the y-intercepts. One thing we didn't talk about yesterday was like the multiplicities of vertical asymptotes. And we talked about vertical asymptotes. We just didn't really talk about what happens if the multiplicity of a vertical asymptote is different than just one. And here's what happens. If you have a vertical asymptote that has an even multiplicity, both ends of on either side of the asymptote are going to go the same direction, right? So with even multiplicities, the asymptote, the graph will go in the same direction on either side of the asymptote. So they either both go up or they both go down. And you can see down here that these are even multiplicities because they're raised to the second power. Whereas over here, the multiplicities are 1 because they're raised to the first power. If your vertical asymptotes have an odd multiplicity, then they're going to go opposite directions on either side of the asymptote. So one side will go down and one side will go up. So this is something we hadn't talked about yesterday, but it is an important thing to know. Here is the horizontal asymptote information. So whether the degree of the numerator is less than the degree of the denominator, equal to, or greater than, it's going to result in different things. So if your degrees are the same, you take the ratio of the leading coefficients. In this case, there was a horizontal asymptote at 2 because the leading coefficient on top is a 2 and on bottom is a 1. So it's 2 over 1, which is 2. Here, the degree on top was smaller than the degree on the bottom. So there's a horizontal asymptote at 0. And here, the degree on top is bigger than the degree on the bottom. So there is no horizontal asymptote at all. So you'll notice as the function leaves the page, it's not tending towards anything. It's not leveling out. It's just going all willy-nilly. And then finally, oblique asymptotes. Those are going to happen when the degree of the numerator is exactly 1 higher than the degree of the denominator, and it's y equals the quotient after doing long division. So here's a picture right here of what an oblique asymptote looks like. And you cannot have an oblique asymptote and a horizontal asymptote. They are not compatible. You cannot have both. The reason you can't have both is in order to have an oblique asymptote, your numerator has to be greater than your denominator. The degree of your numerator has to be greater than the degree of the denominator. And if that's true, there's no horizontal asymptote. So either you have a horizontal asymptote or you have an oblique asymptote, or you have neither of those, but you cannot have both. All right, so now that you have this for your reference, all right, let's do some graphing. First things first, we need to factor. So this guy here, he factors into 2x all over x minus 3 times x plus 1. To find the domain of a function, we're taking the denominator and we're setting the denominator equal to 0, and we're taking those values out of our domain, because wherever the denominator is equal to 0 cannot be within our domain. So x cannot be equal to 3, and x cannot be equal to -1. Writing this in interval notation, we are excluding -1 and we are excluding 3. So the interval notation, we have -infinity down there, +infinity up here. -infinity to -1, we pluck -1 out. Then we go from -1 to 3, and we pluck 3 out. And then we go from 3 to infinity. So that is our domain. It's just where the denominator is equal to 0, we take those values out. For the x and y intercepts, we're going to find the x-intercepts. We're also going to find the multiplicities of those x-intercepts, because the multiplicities, the way that they affected the x-intercepts of polynomials, they're going to have that same effect with rational functions. So with polynomials, if the multiplicity was even, we bounced off the x-axis. And if it was odd, we crossed through the x-axis. It's the same exact process with rational functions. Even multiplicities will bounce and odd multiplicities will pass through. So with, let's see, x-intercepts. With x-intercepts, we're looking at where that numerator is equal to 0. I'll just write the entire function here, but we're only looking at the numerator. So that gives us the 0 or the x-intercept x equal to 0. It's only raised to the power of 1, so its multiplicity is 1. And that's going to mean that we cross at that x-intercept. Now I'm going to scroll down here and I'm going to write that. I'm going to write x-intercept at x equals 0. It has a multiplicity of 1, which means that we're going to cross the x-axis there. I'm going to write it down there. Every time I do something after the domain, everything in steps 2 through 4, I'm going to be making notes down here for when I go to graph. Because I want all that information to be in the same location when I finally graph my function. For the y-intercept, we're plugging 0 into this function. So we're finding f of 0. That's going to be 2 times 0 all over 0 squared minus 2 times 0 minus 3. So that's going to be 0 over -3, which is just 0. So there's a y-intercept at y equals 0. And this is something that we could have seen coming, because we had x equals 0 as an x-intercept. And every time we have x equals 0 as an x-intercept, y equals 0 will be a y-intercept. For the vertical asymptotes, we are looking at the denominator after things have canceled. Now, nothing canceled in this problem, so we're just looking at the denominator. Anything that makes the denominator 0 will be a vertical asymptote. So x equals 3 is going to be a vertical asymptote, and x equals -1 will be a vertical asymptote. And something to note here, the multiplicity of each of these is 1. What that's going to mean for us is that on either side of each of these asymptotes, the function is going to go in the opposite direction. So if I look up here with the odd multiplicities, they're going to go in opposite directions as they hug the asymptote. So I'm going to write opposite directions. On both of these. So that I know when I look at my graph that on either side of them, they should be going in opposite directions. For horizontal asymptotes, I'm looking at the degree of the numerator versus the degree of the denominator. So if I look up here, the degree of the numerator is 1. The degree of the denominator is 2. So the degree of the numerator is less than the degree of the denominator. And that means there's a horizontal asymptote at y equals 0. Now, the sign chart is somewhere where I differ from the way that the MyLab has you do it. What MyLab is going to have you do, and there's no way for you to take this out of these problems, it's just what they are. MyLab is going to have you take different x values and plug those x values into the function and find out the y values there. For me, that's being a little too specific. I think that what I hope for you to get out of this section is not the ability to replicate the exact graph. I don't need you to be able to perfectly graph these rational functions. I want you to know what the properties are and how the general behavior of the graph is. But anyways, on MyLab, it's going to have you plug in x values here to get y values out. You're going to have to do it. You'll see it when you get on there. But for us, for graphing, I suggest making a sign chart. And there's going to be multiple choice questions for you to pick the graph. So you can still use this sign chart to help you pick the graph. So I'm going to take my fully factored rational function, and I'm going to make a sign chart. Now, we don't have an inequality here, so it's not like we're not choosing negatives or positives. We're just going to use the information about negatives and positives, because we know if we do a sign chart on this, if it's negative, that means it's below the x-axis. And if it's positive, we know we're above the x-axis there. So we're going to use that information to help us decide what our graph is going to look like, where our graph exists. So we get x equal to 0, x equal to 3, x equal to -1. Okay, we have -1, 0, 3. I'll go ahead and choose test values everywhere, but you can also use that trick we learned yesterday to only have to use test values once, if you would like. So let's see. Okay. I'm going to plug my test value. I'm going to plug my test value in here. I'm going to ignore the 2. I'm just going to include the 2 as part of the factor for the numerator. If it were a -2 up here, I would make sure I put the negative in on each of these, but it's a positive number. It's not going to change the sign of anything. So -2 in the numerator makes the numerator negative. -2 minus 3 is negative. -2 plus 1 is negative. 3 negatives make a negative. If I'm using my trick that I learned yesterday, I'm looking at the multiplicity of each of these zeros, and the multiplicity of each of them is odd, which means that at every single 0, it's going to change sign. So it should go negative, positive, negative, positive. But I'll do the full long way just to be sure. So taking our test value -0.5, plugging it into each of our factors, we get a negative in the numerator. -0.5 minus 3 is negative, and -0.5 plus 1 is positive 0.5, so it's positive. 2 negatives make a positive. 1 in the numerator is a positive. 1 minus 3 is a negative. 1 plus 1 is positive. 1 negative makes a negative. 4 in the numerator gives us a positive. 4 minus 3 is positive. 4 plus 1 is positive. All positives make a positive. So with the negatives, I know that we're going to be below the x-axis. And with the positives, we're going to be above the x-axis. So really, really quickly, below the x-axis is this area. Above the x-axis is this area. So what we are going to end up doing, and I'm going to delete these colors because those aren't going to help us very much. What we're going to be doing is we're going to be splitting up our grid and determining, based on our sign chart, whether the graph in that area should be above the x-axis or below the x-axis. So between -∞ and -1, we should be below the x-axis. And then again, from 0 to 3, we should be below the x-axis. Between -1 and 0, we should be above the x-axis. And then from 3 to infinity, we should be above the x-axis. Once again, this green area right here that I've highlighted, that is the above the x-axis part. And this area down here is the below. You know what? Maybe I'll just leave it there for a second. I'll go ahead and just leave that because I think that might help a little bit. I can always delete it later. I'll delete it once my graph is complete. All right, so x-intercept. We have one x-intercept at x equals 0. We're going to cross at that x-intercept. So that's right here. It's also going to be our y-intercept. There's a vertical asymptote at 3 and -1. So I'm drawing in my asymptote there. Two asymptotes. So those are my vertical ones. This one's at x equals -1. This one's at x equals 3. And then we have a horizontal asymptote at y equals 0. here's how the shape of the graph works, right? I'm about to draw two different things. Don't draw both of these. Just wait for a second for me to give the correct answer. So we have a choice between either that or this, right? So either it's going to make this shape here, or it's going to make this shape here. And we have information down here on whether or not it should be above or below the x-axis. Which one do we think it is? This is choice 1, option 1, and this is option 2. Should it be option 1 or should it be option 2? You guys got it? Yeah. So if we look here, this is supposed to be below. It says below the x-axis. So it can't be this one. Goodbye. It has to be that guy right there. Notice that when I'm drawing this in, I am hugging each of these asymptotes. I'm hugging the horizontal and I'm hugging the vertical. Now, there are two ways for me to figure out what's going on the other side. I know that I'm supposed to be above the x-axis in this little range right here, like I'm supposed to be above. But additionally, I know that at -1, I'm supposed to be going opposite directions on either side of the asymptote. So if I'm going down here, I have to be going up in this direction. I know at this intercept, I am supposed to pass through because the multiplicity is 1. And that also makes sense because I'm supposed to be below the x-axis after that point. So I'm going to go through, hit, and then let's try it again. And then I'm going to hug the asymptote going down. Notice that in this entire range right here, we are below the x-axis. In this range right here, where we said we would be above, we are above the x-axis. Finally, we're choosing between here and here. And there's two ways that you could choose which of these is correct. There's two ways to choose, but this one's option 1 and this one is option 2. Is it option 1 or option 2? I see it. I was gonna see if anyone else got it too. It's 1. It's 1 for 2 reasons. There's 2 reasons, and excellent work, guys. I'm so proud of you guys. There's 2 reasons that it's 1. First reason is on either side of this asymptote, because it had a multiplicity of 1, it needs to go in opposite directions. So that's one way we could have figured it out. Second way we could have figured it out is because it's supposed to be above. So it's supposed to be in this green area here. So now let me just like delete that color and bam, that's the graph. There she is. Just like that. Right? Thank you. I'm glad you feel that way. I might leave that color in there. I've not done this color this way before, but now I kind of like it. And I think I'm going to go tell my husband after I'm done teaching. But no, I really enjoy doing these rational graphs. I think like there's a lot of steps to it, but it's kind of therapeutic to like build a graph, in my opinion. I know not everybody feels that way, but are there any questions on this one before I go to the next problem? One problem, lots of clues. And I feel like that's why I would like word problems. That's why I like really lengthy problems, because it's like it feels like you're a detective and you're like, I'm going to take all these pieces that I've collected and now I'm going to make a conclusion based upon all the pieces that I have. That is what I love about math. It makes you feel like you're like a number detective. Math Criminal Minds. Yes, absolutely. It's Math Criminal Minds. Have I ever seen Criminal Minds? No. But do I assume that it is a show where there's detectives? Yes, that is what I assume Criminal Minds is. Okay. I'm going to go ahead and scroll. We're going to do this one. I know this one looks kind of nasty. We will be okay. So looking at here, nothing cancels. All right, nothing cancels. Don't need to worry about there being holes or anything. That's good. It's already factored, even better. So finding the domain of the function, we just need the denominator to not be equal to 0. So that means we can't have x be equal to 1, and we cannot have x be equal to -6. We've seen this song and dance many a time at this point. I probably don't even need to draw this little number line now because you've seen it happen too many times. But I just like drawing number lines and I like making squigglies. So I will continue. All right, so we go from -infinity to -6, -6 to 1, 1 to infinity. If you guys aren't absolute pros at finding domain of rational functions by the end of this, that I will be disappointed. You should be absolute pros at finding the domain of rational functions by the end of this. Even if you haven't done a single problem yourself, you have seen me do it so many times. Okay. X-intercepts. We're taking the numerator and we're finding where it's equal to 0. Here we get x equal to -3, and the multiplicity here on that 0 is 2. Here we have x equal to 2, and the multiplicity on that 0 is 1. I'm going to come down to here, x-intercept at, so I have x equals -3. The multiplicity was 2, which means it should bounce. I also have x equal to 2. The multiplicity is 1, which means it should cross. Now, when you get to calculus, there's a section that you do called curve sketching, and you end up doing a lot of this again. And what you learn from that calculus section is that being organized is your best friend. So you see me reorganizing my work down here. That's a really good habit to get into when you have a multi-step problem like this, is as you're going along, writing down the key facts. Like I'm finding key information here, but if I don't highlight it and then rewrite it down here, it's going to get all jumbled together and lost. So organizing your work is your best friend. For the y-intercept, I'm plugging in 0 to this function up here. So I have r of 0, that's plugging in 0. 0 plus 3 quantity squared times 0 minus 2, all over 0 minus 1 quantity squared times 0 plus 6. So we get 9 times -2. -1 squared is going to be 1, and then 6. So -18 divided by 6, that's -3. We have a y-intercept at y equals -3. I also like to think that I'm like one of the best, like one of my strengths in teaching calculus is my curve sketching. I am a good teacher of curve sketching. I'm just gonna say. You can think that maybe I don't do a great job on it. I'm gonna say I think I do. We should all be proud of something. Okay. Next, finding all the asymptotes. We need vertical. We need to figure out if there's horizontal / oblique. And then there are no holes in the graph. We know there aren't any holes in the graph because nothing canceled. So vertical asymptotes first. We're looking at the denominator. So we have x minus 1 quantity squared times x plus 6. Here we get x equal to 1. And notice that the multiplicity on this vertical asymptote is 2. The multiplicity is 2. For the next one, we have -6, and the multiplicity is 1. So there are vertical asymptotes at 1 and at -6. So I'm coming down here. Ooh. There's a vertical asymptote at 1, and because the multiplicity is even, they're going to go in the same direction, right? They're going to go in the same direction. So multiplicity 2, this is going to be same direction. Can I fit it in? Yes. We have another vertical asymptote at -6. Because the multiplicity was 1, they're going to go in opposite directions. The next thing is figuring out whether or not there are horizontal asymptotes. Not asymptotes. There's only ever going to be one if there is one. And I will be scrolling back down here, so I'm going to scroll up for a second, but I will scroll back down. So here's the thing. This thing is all factored, and like hell, I'm gonna FOIL that all out. That's so obnoxious. I am not going to FOIL that entire thing out. But what we have done in the past is we have found the leading coefficient, or the leading term, by doing a little trick. So if you remember, we did this trick where it was like, for each factor, we would cancel out. So we would like eliminate everything except for the highest term. And that was how we found the leading term. That's what we're going to do. That's what we're going to do. We're going to cancel everything out to find, except for the highest, everything except for the x's on each term. We're just going to pretend they're not there. It's not really canceling. It's not canceling at all, but we're going to pretend everything except for the x's is gone, and then that'll tell us what the leading term is. So the leading term in the leading term in the numerator. Okay, so if we get rid of the +3, then we have x squared. If we get rid of the -2, we just have an x. So it's an x cubed. In the denominator, the leading term, if we get rid of the -1, you have an x squared. And if you get rid of the +6, you have an x. So it's an x cubed. So if you kind of put it all together, so you have x cubed over x cubed, the degree of the numerator is the same as the degree of the denominator, which means that we're looking for a ratio of the leading coefficients. There's a 1 in the numerator and a 1 in the denominator that's like secret, super secret. Nobody knows about it, 1 over 1 is 1. So let me rewrite everything I've said. The degree of the numerator is equal to the degree of the denominator, which means there's a horizontal asymptote at y equals ratio of leading coefficients. So there's a horizontal asymptote at y equals 1 over 1. And that 1 over 1 I'm getting from right here. 1 over 1 leading coefficients. I go horizontal asymptote at y equals 1. And I will write that right down here. Horizontal asymptote at y equals 1. Finally, we have a sign chart we need to do. So we have x plus 3 squared times x minus 2 all over. Ooh, I wonder if my husband remembered to pick up dog poop. Our gardeners are coming today, and I just remembered that. And I don't know if he remembered to do that. Give me 1 second. Let me text him to make sure. My bad. Okay. And that's not to say that I don't pick up dog poop, just in case you think I'm like, oh, I can't, I'm too good to pick up dog poop. It's not, it is 100% not that. It's just the timing today he was going to do it. And I just don't know if it actually happened because things get crazy when your baby won't sleep. All going a little bit nuts here. Okay, we're making our sign chart. So we have 4 different, ooh. Oh, come on, make me a straight line. Why are you doing this to me? We have 4 different zeros here. We have -3, 2, 1, and -6. So -6, -3, 1, and 2. Choosing test values. We have -7. I'll do -4, 0, 1.5, and 3. You could also use your trick here. Totally use your trick here. Furthermore, when I look at these factors, when I go to plug in, I know for certain that this factor here and this factor here are always going to be positive no matter what I plug into them. Because even if I plug in -7, like if I plug in -7 to this one, -7 plus 3 is -4. But when I square it, -4 squared will become +16. It doesn't matter what I plug in. Once it's squared, it becomes positive. So I'm just going to plug in, and it's the same thing for the bottom one too. I'm just going to plug in positives immediately for those before I copy paste this into every one of these. Oops, no, not that. Not that. So all we really need to plug into are the x minus 2s and the x plus 6s. Now, here's the thing. Here's the thing. -3, this 0 has -3. Highlight it. And this 0 right here, that one has 1. Because these guys right here have even multiplicities, what should happen is it should switch signs when we cross over -6, but it shouldn't switch signs at -3, and it shouldn't switch signs at 1, but then it will switch signs at 2. But we'll do it the long way. -7 minus 2, that's negative. -7 plus 6, that's negative. Oh my gosh, dogs. Why are you the worst? Oh, now the gardeners are here. Oh no. All right, not my problem. Not my problem. All right, so 2 negatives make a positive. -4 minus 2 is a negative. So my claim right now is that it will switch signs, so it should be negative here. And then -4 plus 6, that's +2. And one negative makes a negative, so it did switch sign. And then I'm going to claim that it stays negative here and here because these guys have even multiplicities. Plugging in 0, 0 minus 2 is negative. 0 plus 6 is positive. One negative makes a negative. 1.5 minus 2 is negative. 1.5 plus 6 is positive. One negative makes a negative. 3 minus 2, and I'm going to claim it changes to positive here because 2 has an odd multiplicity. So 3 minus 2 is 1, which is positive. 3 plus 6 is 9, which is positive. All positives make a positive. Ugh, so much work. All right, so where the positives are, we are above the x-axis. And where the negatives are, we are below the x-axis. So I can come down below. I am above the x-axis from -infinity through -6. And then again from 2 to infinity. And then the entire in between, I should be below. I should be below. Ooh. Okay, time to plot stuff. So I have an x-intercept at -3, and this one I need to bounce at, right? This one I need to bounce, and I need to remember that I should be bouncing on this one. I could make some notes to remind myself, like I could make like a little bouncy, because I don't know if I'm coming from above or below, but I can make a little note like that to remind myself that I bounce. I typically don't make, I'm not going to make a note that I'm crossing, but I will make a note that I bounce, because crossing is the standard. At x equals 2, we have another x-intercept. We have a y-intercept at -3. We have two vertical asymptotes, one at 1 and one at -6. There's -6. Here's 1. And then let me label those. -6 and 1. And then we have a horizontal asymptote at y equals 1. At y equals 1. So with the x equals 1 asymptote, what's really important here is that because this has multiplicity 2, when we do it, it should either look like this, or it should look like this. They should go in the same direction. Whereas with the x equals -6 asymptote, we should be going in opposite directions. So we should be looking at either this, this and this, that's one option, or this and that is the other option. Okay. For my first little, I don't want to say quadrant, but my first area here, should it be this or should it be this? This is option 1, this is option 2. Option 1 or option 2 for the first area? Yeah. You guys are getting it. You guys are getting it. Love it. Okay, so it has to be this one for a bunch of reasons. One, because it's above the x-axis, right? So this is the only region that's above. 2, if it were in this region here, it would have to cross the x-axis. And if you cross the x-axis, then you're an x-intercept. I also don't like the way the shape of that one turned out. And we know what the x-intercepts are, and there's not one at -8 or -7. Now, we know that -6, this one, they should be going in opposite directions. So if I'm going up here, I know for certain that I need to be going down here. Additionally, I know I'm supposed to be below the x-axis anyway, so that makes sense. So the way that I bounce, it's definitely going to be bouncing down below, so I can kind of take out those little marks. Oops. Do this a little better. I'm going to bounce. I'm going to make sure I hit the y-intercept, and I'm going down. So I've bounced, I've hit the y-intercept, going down, I'm below the x-axis the entire time. I know with this asymptote, because it has a multiplicity of 2, that we should be going in the same direction. So I know that I'm supposed to be going this way. Additionally, I know I'm supposed to cross at this x-intercept, and then I need to hug the asymptote. So going through, that's a little square for my taste. That's still a little square. Oh well. Close enough. There it is. Beautiful. Easy peasy, beautiful, breezy cover girl or something. Okay. So we have, okay. We have time to do 2 more of these examples. We have 3 problems left, but there's 2 examples. If you need this on the screen still, now would be a great time to take a photo of it with your cell phone, because I'm going to scroll some and give you like 5, 4, as long as it takes me to take the sip of coffee until I scroll. Okay. So this problem here is going to have a hole. This problem down here is going to have an oblique asymptote. And this last problem, I think we're definitely going to want to do because it's different than all the others. This one here, you write a function based upon the graph. So I'm going to say, I'm going to executive decision here. We're definitely doing this one. The question is, do you guys want to do an oblique asymptote problem, or do you want to do a problem where there's a hole in the graph? I will take votes starting now. So your options are 1, yes, 1, the whole problem, or 2, oblique asymptote. And if I have my way, it's going to be the whole problem. So, I mean, I don't know if I even put an oblique asymptote problem on there. Let's do the whole problem. I'll use my exact, yeah, let's do that. Let's do that. Alejandro said whole, we're doing the whole problem. I'll blame it on Alejandro. Just kidding. No, you guys want it. You guys want this one. I think this is a good choice. I think this one is. So we're going to factor. I know there's a GCF of 4, so I'm going to factor that out of the numerator. I'm going to go a little quick through this one. I'm going to go a little quickly through this one purely because I want to make sure we can get to that very last problem on there. So I'm just going to, factor this like any good math, come on, stop that. Any good math professor does. X plus 5, X, why are you doing that? Why is it, stop. All right. Tough jury duty. Tough jury. All right, here's what happens. We factor it. The x plus 5s, they cancel. What that means is that there is a hole at x equals -5. We will come back to that idea. We're going to come back to that idea in a little while. So we have 4 over x minus 1. Sorry, not 4 times x minus 1 all over x plus 2. I'm not going to do the domain on this because you've seen me do domain a million times. I don't need to do another domain. You know what the domain, the only thing I need to say about the domain is that you use this one. So maybe I won't do the whole interval notation, but I will say that you take this guy and you take out both of the values. So you go to the unfactored, the uncanceled version. Stop trying to paste. Delete. All right, X and Y intercepts. For the X-intercepts, you're looking at this completely factored form. So the X-intercept is where that numerator is equal to 0. So we have X equal to 1, and the multiplicity is 1. So X-intercept at X equals 1, multiplicity of 1, which means we're crossing. For the Y-intercept, we're plugging in 0. I'm just going to tell you that it comes out to be -2. Okay, I have to kind of go a little bit quick here if I want to get through both these problems. So just going to kind of tell you. For the vertical asymptote, you are only looking at the completely factored and canceled form. So you don't have an asymptote at -5. You do have one at -2. And the multiplicity is 1. So it's going to go opposite directions. And I'm kind of rushing. I really want to make sure we get through. The horizontal asymptote, the degree of the numerator and the degree of the denominator are the same. So it's a ratio of the leading coefficients. It's going to come out to be 4, because it's going to be 4 over 1. So here's the 4, here's the 1, 4 over 1 is 4. So there's a horizontal asymptote at y equals 4. And then we have the hole that we need to deal with. We know that that hole happens at -5 for the X value. We need to find this Y value, and we find that by plugging in -5 to this guy. So we do Y equals 4 times, now we're plugging in -5, -5 minus 1, and then -5 plus 2 on the bottom. This is going to come out to be 8. So there's a hole at -5, 8. When you go to do the sign chart, I'm going to really cheat here. You only use this guy. You don't need to use the uncanceled form. You can use this canceled form here. So you have X equal to 1, you have X equal to -2. Like I said, I'm just going to kind of cheat and tell you what it turns out to be. So we have -2, we have 1. This is going to turn out to be positive. This will turn out to be negative. This will turn out to be positive. So we have above, above, and below. And that is all we need to graph. So here to here, that is above. From 1 to infinity is above. And in this region right here, we are below. There's an X-intercept at 1. There's a Y-intercept. No, where was the Y-intercept? At -2. I forgot to write that down. Y-intercept at Y equals -2. There's a vertical asymptote at -2. Oh my goodness. Those noises are very loud. And a horizontal asymptote at Y equals 4. Now, unfortunately, while creating this problem, this problem ends up being a little weird, but it's fine. I'll show you once it's done. There's a hole at -5, 8. -5, 8. So there's a hole right here, which means I need to pass through that hole. I know that if I'm above the x-axis, that means that I'm in this region here. Now, normally I would like to draw my curve like that. This problem just so happened to come out a little bit weird so that you can't quite draw the asymptotic behavior over here. It would get close to the asymptote, it just doesn't happen on screen. Over here, we know we should be below the x-axis, so we're going to come through here like that, bam. Easy peasy, beautiful cover girl. It's above where it's supposed to be above, and it's below where it's supposed to be below. The big thing is with these holes, you should be passing through them as if they were a point on the graph, right? You pass through it, it's just that there's a hole in the graph. Oh my gosh, that is so loud. That is obnoxious. Okay. Really, guys? Okay. Again, I'm moving fast. I need to move to this last problem. I'm going to go through it very, very quickly. That's so annoying. I'm going to be moving screens real quick. So we're going down to this very last problem. We need to determine the equation of this graph. You might think that it's impossible, but it is not. We are given enough information to do this. First things first, we have two different asymptotes. They're not drawn in there, but we know that they're there. So we have a vertical asymptote at x equals -1, and we know its multiplicity has to be odd because it's hugged in different directions. We have another vertical asymptote here at 2. And we go in the same direction on either side, which means the multiplicity needs to be even. When I go to set up my rational function, I'm going to put a constant in the numerator because we're going to need a constant up there. These vertical asymptotes, those come from the denominator, right? The vertical asymptotes we get from the denominator. So for -1, we would have x plus 1. It's raised to an odd multiplicity, so I'll just leave it at 1. For 2, that would be x minus 2. And it says an even multiplicity, so I'm going to square it. Additionally, we have 2 x-intercepts. We have one x-intercept right here. It's at x equals -2. And we cross through it, so its multiplicity is 1. Additionally, we have another x-intercept at x equals 3. We also pass through it there, so the multiplicity is 1. So loud. The x-intercepts come from the numerator. So for -2, this is going to be x plus 2, multiplicity of 1. For 3, we have x minus 3, multiplicity of 1. The only thing left to do is solve for this a value. We can do that using the y-intercept. So this y-intercept is at 0, -2, and we can plug that point in for x and y, and then solve for a. So x is going to be 0, y is going to be -2. So we take -2, leaving A alone. 0 plus 2, 0 minus 3. Fine. 0 plus 1, 0 minus 2 quantity squared. On top, 2 times -3 is -6. So we have -6a. On the bottom, 1 times -2 squared is going to be 4. To get rid of the 4 in the denominator, I can multiply both sides by 4. I get -8 equal to -6a. Dividing both sides by -6. Those -6's cancel. 8 over 6 is equal to a. If we reduce that, it's going to be 4 over 3. Ugh, so much work, but we're there. All we have to do is replace a. If you have a fraction, the 4 is going to go in the numerator, the 3 will go in the denominator. So we're taking this guy right here, and we're just plugging in the a value. So we have y equals, we have 4 in the numerator, then it's x plus 2 times x minus 3 all over. The 3 from the a goes in the denominator. X plus 1, x minus 2, quantity squared. Bada bing, bada boom, done. Oof. Okay, sorry it went over. I know I'm awful. But again, this 4 right here goes right there. And then the 3 went in the denominator. So big process on these. X-intercepts give you the numerator. Your asymptotes give you your denominator. And then you can use the y-intercept to solve for a. That's the big idea. And with that, that is everything I have for you. If you have questions, I will stick around to answer them. Otherwise, I hope you all have a fantastic Wednesday. Don't come to class tomorrow. I won't be here. Nobody will. Enjoy your long weekend, and I'll stop the recording right here. But again, if you have questions, you can stick around.